Integration of standard functions, part 3. So integrating the cosine of an angle that's a linear function and in radians. So this is positive cosine, so we're here in our little diagram, and instead of going clockwise, which was for differentiation, we're going anti-clockwise. So we start from C and we end up on S, so we're going to get positive sine. Same angle, ax plus b, you divide by the coefficient of x plus a constant of integration. And then for sine, so we're starting here and it's positive sine, going in this direction takes us to minus cosine there. Same angle, ax plus b, linear function, and then we divide by the coefficient of x. Now when we were differentiating with all of the functions for differentiation that we've looked at, we had things like cos, and then the angle was any function. We were doing things like this, d by dx. So you might wonder, can I do the integral of cos any function? Unfortunately, no, you can't do that. That was fine for differentiation, but not here. When we're integrating, the best we can do here is a linear function of x. Now the remaining trig functions are in the formula book, and we can modify these slightly to have like ax plus b for the angle instead of just kx. So as an example, if we look at secant squared and we're integrating, I can modify the formula here to secant squared ax plus b, and that will give tan, same angle, ax plus b, and once again we're dividing by the coefficient of x, and this is slightly more useful than the one that's in the formula book. But again, there's no such thing as, is there a formula for when we're integrating secant squared, so any possible function of x here for the angle? There isn't. So a couple of modified formulae from the formula book, from the Edexcel formula book. Okay, so integrating tan will give ln secant with the same angle. So integrating tan of this angle will give ln secant, there, ln secant, same angle, but then we have to divide by the coefficient. It's not x in this case, we're using theta, so the coefficient of theta is 2. We have to divide by that, so multiplying by a half does the same thing, plus c. So we're just using the formula here. Make sure you use the modulus as well. It's more important when you use the modulus when you have limits to substitute in. So here we're integrating 3 cosec 4x, so we need to find the standard integral for cosec from the formula book. So integrating cosec will give us a minus, and then it's a ln, and then it's cosec plus cot. Or instead of using this, we can use ln tan, but then we have to modify the angle in there. It's not the same angle. Okay, so I'm going to stick with this one, this formula here. Okay, so we have ln modulus. Again, the modulus you have to use if you have limits. If you don't have limits, you can use normal rounded brackets here, but I'm going to stick with the modulus. So we've got cosec 4x plus cot. We're using the same angle throughout, 4x cot 4x, like so. We have to put a minus in. I'll come back to that in a minute. We're dividing by the coefficient of x, which is 4. Was multiplying by 3, I have to still multiply by 3. There's my minus, and I need a constant of integration. Integrating cosec squared. In the formula book, there is no cosec squared as a standard function that we can integrate. If we look at the standard derivatives, we can see there is a cosec squared on this side. Now remember, going in this direction means you're differentiating, but in this direction, in reverse order, we are integrating. And the same thing is true here. In this direction, if we're integrating, then in this direction we're differentiating. So we can use these formulae as standard derivatives, just as we can use these for standard integrals. So if we integrate cosec squared, we get cot. So if I stick with the formula from the formula book first, so differentiating cot gives minus cosec squared, and then if I modify the angle kx to any angle f of x, which we can do with derivatives. So now what we have to do is rearrange this, because we're differentiating in this direction, and if we integrate the right hand side we get the left hand side. So we need to rewrite this as an integral rather than a derivative. So we need to reverse the order of this. Okay, so now I've reversed the order, so the right hand side is here, the left hand side is here. I'll put the dx and the constants in afterwards. It's almost the same as what we want to integrate. Now one thing you can do when you're integrating, if you have a standard formula or some result written down, you can multiply or divide both sides by a constant. Not adding or subtracting, but multiplying or dividing by a constant on both sides is allowed. What you can't do is multiply or divide by a function of x or any x term, but constants are allowed. So I need to get rid of this minus 2. There's no minus 2 in the question there. So if I divide both sides by minus 2, so that will go if I divide by minus 2. Dividing by minus 2 on this side, and then just simplifying at the end. So integrating all of this will give us minus a half cot 2x minus 4 plus a constant of integration. For practice, try these questions.